So let's put everything we've learned together. Let's do another example. We have a matrix A. We want to know the rank of A. We want to know the dimension of the row space of A, the dimension of the column space of A. We want to find a basis for the row space of A. We want to find a basis for the column space of A. If you know what you're doing, if you understand the theory we just developed, we can learn all this information very quickly and easily once we get the reduced row echelon form of A. Okay? So my first step is I'm going to take matrix A and I'm going to find its reduced row echelon form. And we want to find the reduced row echelon form of the matrix. And there we have it. So the reduced row echelon form of A is equal to 1, 0, 7 twelfths, 0, 1, 1/3, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. The rank of the matrix is just the number of non-zero rows, or another way to characterize it would be the number of columns with leading entries in them when in reduced row echelon form. Or another way to characterize it would be the number of leading entries in the matrix when in row echelon form or in reduced row echelon form. Okay. We have 2 leading entries, which means we have 2 non-zero rows when the matrix is in row echelon form. It also means we have 2 columns with a leading entry in them. So the rank is 2. The dimension of the row space is equal to the rank, so it's also 2. The dimension of the column space is equal to the rank, so it's also 2. Remember, the rank, the dimension of the row space, the dimension of a column space of a matrix are always equal to each other. All right? Now, to find a basis for the row space, remember when we perform elementary row operations, the row space stays the same. So the row space of A and the row space of the reduced row echelon form of A are the same. And the reduced row echelon form of A is much easier to work with. All non-zero rows in the reduced row echelon form of A are linearly independent. So for the basis of the row space of A, I could just take the non-zero rows of the reduced row echelon form of A. So the first non-zero row is 1, 0, 7 twelfths. And the second non-zero row is 0, 1, 1/3. And I have 2 vectors, which is what I expected because I know the dimension of the row space of A is 2. Okay? As for the basis for the column space of A, I have, if I was to use this in finding the solution to a homogeneous equation, I would have 1 free variable. I don't want any free variables because that means my vectors wouldn't be linearly independent. So I'm going to get rid of that last column with a free variable, just mentally. That leaves me with the 2 columns with a leading entry in them. Okay. If I go back to my original matrix and find those same first 2 columns, these first 2 columns here, I know when I take their reduced row echelon form, they will each have a leading entry, which means they will be linearly independent. It's that last column that's the problem. When I find the reduced row echelon form, I can see that that last column is giving me a free variable. Okay, since I do not have a leading entry in column 3. And so the columns of my original matrix that correspond to the columns in my reduced row echelon matrix with leading entries are going to be my basis for my column space. So the first column has a leading entry when I'm in row echelon form. So the first column of matrix A is going to be in the basis of the column space. And so that's -4, 4, -4, -4, 4. Lots of 4s. Okay. The second column of the reduced row echelon form of A has a leading entry in it. So the second column of my original matrix A is going to be in the basis. I'm going to add it to my basis for my column space of A. So that vector is -2, 8, 4, -8, 8. And the last column of the reducer echelon form of A does not have a leading entry in it, which means I will not add this last column of matrix A to my basis. I end up with 2 vectors in my basis for the column space of A. That makes sense because I know the dimension of the column space of A is equal to the rank, which is 2. I should have 2 vectors in the basis for the column space of A.